is probably even larger in the Eastern Pacific because we have much more convective clouds. It's warm here, so that will trigger convective events in the Western Pacific. And in the Eastern Pacific, yeah, we have clouds. We have stratus clouds, low-level clouds. But overall, I don't have the picture here, I think, right now, but the solar radiation is actually probably stronger even in the Eastern Pacific compared to the Western Pacific, so cannot be used as a reason why it's cooler here. So it has to be ocean dynamics somehow that cools off the Eastern Pacific. Partially upwelling, partially from advection from the northern latitudes at the equator. And so we look at this is now a different month, average for a different month, but it's the same, we don't care. This is now the sea surface temperature, because the land is here masked out, because we are interested in the ocean right now. Average for July, but again, if you take January, the picture, apart from the hemispheres, would show different behavior, so it would be much colder in the northern hemisphere and warmer in the southern hemisphere if we take January. But the equatorial picture looks very similar. So what we see, of course, is cool temperatures in the exotropics and polar region, and warm temperatures in the tropical region. Of course, we know why. Because on average, the tropical regions receive more solar energy than the exotropical regions. So there's no big surprise in that. However, we see there is this, again, what we've just noted, there's this cool region here. And actually the same we see in the Atlantic, but it's missing in the Indian Ocean. So we mentioned this already, it's probably upwelling. So what is happening is that let's say here's the equator, and to the north and south at around 30 degrees, this is 30 north and 30 south. We will discuss this later in the course actually, what is the typical situation, but maybe you probably know what is the typical pressure distribution if you think of just meridional changes between equator and 30 north and 30 south. Where do we have high pressure and where do we have low pressure?
Equator. High pressure. High pressure.
At the equator, we have lower, at the surface, low or high pressure?
Low.
Low. The intertropical convergence zone is close there. The warmest region. And here we have the subtropical high pressure systems. On average. And there's variations from this. But on average, that's the case. If you want to think of it as a very simple explanation, actually, why this should be the case, then of course it's much more complicated because of rotation of Earth and so on. But in principle, we can assume that we have the warmest air here, right? In warm air, you know that the change of pressure with height has to be less, according to the hydrostatic equation, than in cold air. So warm air means that in upper levels the pressure will be relatively high compared to the other regions. And that will flow out. This outflowing air causes the pressure at the surface to decrease. So we expect typically in warm air to have a low pressure at the surface and a high pressure in upper levels. And then there's a circulation cell. Of course, this is a local argument, and for the Earth's climate it's a little bit more complicated. But in principle, this argument is very well justified here. So we get the low pressure at the equator, or close to the equator, and the high pressure in the mean in this subtropical high pressure regions. And then what does the wind do? The wind blows in this direction. Because also things we haven't derived properly yet, but anyway, for one thing we know, the geostrophic balance, okay, we are close to the tropics, but as we mentioned, if we are already a little bit away from the equator, the geostrophic balance is quite valid. So the wind will blow, if we have high pressure here and low pressure there, will blow from the east to west. We call this trade winds. This whole area, we have a region of trade winds in the Pacific and in the Atlantic and everywhere in principle. And then there are perturbations to that, but on average it's like that. And then the winds, of course, they converge at the equator and cause rainfall and so on. So the winds do not blow exactly parallel to the line of constant pressure. Can you guess why? They tend to flow from the high pressure to the low pressure. We will derive this also later in this lecture. Surface friction. Surface friction. So at the surface, whereas in the higher levels of the atmosphere, probably we would find it's more or less parallel, the wind, to the isolines of constant pressure. But at the surface, the frictional force would make the flow going from the high pressure to the low pressure. So there's this kind of, we get this flow. So,
excuse me, Professor.
yes?
I was thinking that probably also the rotation will play a role. For example,
Yes.
if you're off the ground, then friction.
No, rotation plays a role. Because the rotation determines us, in the first place, that the winds should be parallel to lines of constant pressure. That's the Coriolis force that we have used there, the equilibrium between pressure gradient force and Coriolis force. So the Earth rotation is important. Otherwise the flow would just go like this, without Earth rotation. So the Earth rotation plays an important role here. Yes. And now, so what is happening? Actually, on the equator, something interesting is happening in general. Because on the equator, where we have this situation that the wind blows here in both directions, north and south of the equator, like that, you probably have done this already in ocean, or saying that there's some Ekman layer in the ocean. So the wind is drawing some winds in the ocean, and there's an Ekman layer. And in this Ekman layer, the flow will be in the ocean, will be like this, at the surface, at the upper levels of the ocean. That means everywhere on the equator, there will be the tendency to get upwelling. So that in principle should cool off the equator. So we have found one reason why the equator should be cold, but it's not really everywhere cold. That's one thing that the trade winds do. The other thing is actually much easier. The fact that we have a continent on the eastern side means that since the wind is trying to push the water over in that direction, then it cannot take the water from the land. So the mass must come from somewhere else. So it comes either from the sides or from the bottom. And all of these mechanisms will cool off the temperature at the equator. If the flow comes, it's always colder. It's colder to the north and it's colder to the south, and in particular it's very cold if we go down. So that makes it quite easy for us to understand why, given the fact that we have trade winds and a continent, makes it cool on this side. In fact, you see that where in an ocean where the continent on the eastern boundary is missing, there's some islands, but there's flow probably around here. So the trade winds that are still there on average, they don't manage to cool it off here. It's not possible. We need the continent. Same thing in the Atlantic. So in fact in the Atlantic we have something like an El Nino also there. Only that its characteristics are slightly different because of the size of the basin. The Pacific is huge, the Atlantic is a little bit smaller. So that explains now why we have this, this situation where we have the cool Eastern Pacific and the warm Western Pacific. And then you can imagine actually, okay, in a schematic how this looks like in the ocean and the atmosphere. A nice schematic is this, that you also find everywhere on the web. So the ocean is essentially driven by the trade winds to move from the surface layers from the east to the west. And then the water is replaced in the east by cooler water, either from the northern and southern latitudes, and in particularly from below the surface, upwelling of cold water, and is pushed over. And so most of the convection will take place where we have the warm waters, because the air is more unstable, and then it's sinking in the Eastern Pacific. Do you know how this circulation is called? Headley? No, it's the other. Walker. The headley would be between, in this direction, the meridional direction. We will discuss this also later. So this is called Walker circulation. Actually, it's not a, whereas headley is a real closed mathematical circulation. You can define it. The Walker circulation is a little bit more. It's not so strict because we cannot really define a stream function. But on average, there is something like this. It's not really a closed circulation, but there is some kind of circulation. Upgoing motion in the Western Pacific, downward motion here. And so the system looks like this. The thermocline, as you can see, is tilted due to that. Get the cold water up here due to upwelling, and then as a response, there is a ocean downwelling here. It's quite interesting, this picture. So actually, if you think about it, the system is under tension. That we need forces to cool off the water here. Because if we get rid of this force, it's clear that the water here, due to the solar radiation, would warm up very quickly. That, in my understanding, that was the initial, would be the normal situation. But we have this kind of a system under tension, where permanently we are pulling up cool water to the surface here, make the surface cooler than it should be under thermodynamic equilibrium conditions. It's very easy to show. If you run a model, you use a static, what we call mixed layer ocean model, which cannot move. So it's just a thermodynamic ocean that is fixed, and you integrate just a thermodynamic equation there. Given the thickness of the ocean, you have heat fluxes from the surface, and that is your ocean in a model. In a model world, you can do what you want. Then you will find the Eastern Pacific will be very warm, of course. Due to the large surface heat fluxes, the Eastern Pacific would be extremely warm. So you need something in those simple models to fix this situation and to cool off the ocean there. So that's the situation. And now it's kind of intuitively clear that perhaps sometimes this breaks down and the Eastern Pacific gets warm, potentially as warm to make the whole surface temperature here having more or less the same temperature. So we can almost guess what is the potential for a big El Nino if we compare the surface temperature difference between Eastern and Western Pacific. So we have here temperatures 23 degrees maybe, and here 28 degrees. So 5 degrees is probably the maximum that we could expect. And then everything should have the same temperature. All the warm water goes all the way.
Professor, excuse me.
Yes.
I ask you, why is it that we're only in the Pacific? Because there is more surface to be heated.
Why is this only happening in the Pacific? It's actually also happening in the Atlantic. But people have been in the past more concerned about the Pacific because there's so much more water there that the teleconnections are just more powerful. So it's simply more important, but it's also happening in the Atlantic. In the Atlantic we have exactly the same phenomenon. Only that it's on shorter time scales, as you can imagine, because of the size of the basin. But we have exactly the same phenomenon, and the season is slightly different when that peaks is slightly different also. So what's happening during any new event? We have said this already. We have this system under tension, and actually it's an interesting thing that we maybe should discuss. That there's an important positive feedback going on. Because the fact that now, given trade winds, there's a tendency to cool off here and to warm up here, right? At the surface. But the cooling here and the warming here means also that again through the hydrostatic equation, we have discussed this before, there's a tendency to have anomalously high pressure here and low pressure there. Simply because of the hydrostatic equation at the surface. So that pushes even more water than from the east to the west. There's a positive feedback between atmosphere and ocean. The ocean cools off the surface, the atmosphere responds to it in a way that even enhances this process. And this is called Bjerknes feedback in the Pacific. Everywhere in principle, but it's most prominent in the Pacific. It's a Bjerknes feedback. You have a positive feedback between the ocean and the atmosphere. And the same Bjerknes feedback is actually at work when an ENSO event is developing, but in the opposite direction. What's happening during any new event is, and we will now, in the theoretical part of this lecture, try to cut that down exactly what's happening during any new event. It's clear that now you weaken a little bit the trade winds. Some perturbation in the trade winds. Something random is happening. We have discussed this in current weather. Maybe some long-lasting. Remember this cyclones on both sides of the Pacific that were present, and Adrian mentioned, maybe this could lead to a El Niño development or something. Some lasting perturbations in the tropic. Maybe they can weaken the trade winds. Now, if you weaken the trade winds, that will then lead to less cool water at the Eastern Pacific due to upwelling. That will cause that the high pressure here is less, and therefore the positive feedback also works in the other direction. Even less water is pushed over, and there's a tendency for the Eastern Pacific to warm up. The Bjerknes feedback that works in the mean state also works for perturbations. We may just reverse the thing, and then the whole, in the case of a strong El Niño event, the whole Pacific basin will be swapped by warm waters, essentially. And then we get convection all over the place, not only anymore in the Western Pacific, but definitely reaching the Central Pacific, and in some occasions even the Eastern Pacific. And the thermocline is much shallower. So why are we so concerned about this? Because of what we call teleconnections. So actually, some of my personal main research area is to understand and to describe and to make use of teleconnection mechanism. Now we have this huge perturbation in the Pacific, and we have seen this already, that may create extratropical waves that influence climate in North America, for example. We have seen this wave already. This was for winter. In winter and summer, teleconnections are different. A very well studied teleconnection is the teleconnection from ENSO to the South Asian monsoon system. So it's very well known for any Indian just also normal people, that when there's an El Nino, that's a critical situation for rainfall. They may expect a large deficit in rainfall when there's a Nino in the South Asian region. So that's a very well established teleconnection. But there are more, and I don't even think that everything that has been analyzed is already on this map. But as you can see, Europe is usually blank. This doesn't mean there's any teleconnection, but the wave train has lost already so much energy that compared to the noise, the weather noise, the ENSO signal may be too weak to really be able to say anything that you expect a warm or cold or wet or dry winter in an El Nino year, even though it's continuously studied. Maybe there is something, some nonlinear impacts. Maybe there is something. Maybe we have to divide the season, cannot just look at a seasonal mean the whole winter. Maybe if we divide from November, December, January, February, we can actually find some signal here. But this is ongoing research. But there is something in Europe that may involve even more complicated things than just the tropospheric wave train, but the influence on the stratosphere actually is discussed very much. So there, even though it's blank here, but in reality this is nowadays very, very much investigated if there's an impact on Europe. But still, yes?
Sorry, but so does it mean that these teleconnections, when they propagate westward, they are due to Kelvin waves carrying information?
Eastward. Eastward. In the tropical regions, yes. In the extratropical, we have discussed it. The extratropical wave train is actually due to a Rossby wave source that is slightly off the equator, maybe here, and then that creates an extratropical Rossby wave, the one that we described with our vorticity equation for the exotropics. That would be responsible for most of the teleconnections in the northern hemisphere in the winter. So the warming in Alaska is a very well-known teleconnection. We will see this actually later. And then these wet conditions too. And you can see one other interesting thing, and we have some kind of indication for this. It seems that the teleconnection to the winter hemisphere is stronger. Well, at least for the northern hemisphere, that's the case. It's much weaker in the southern hemisphere, and then I think there is a clear indication that the teleconnections to the winter hemisphere are stronger. The reason is, at least part of the reason is the existence of stationary waves. Stationary wave can exist only when there is a mean westerly flow, which is definitely and strongly the case in the winter hemisphere. In the summer hemisphere, the westerly flow can be extremely weak, and in some cases prohibit the wave propagation altogether because it's close to zero. And then stationary Rossby waves simply cannot exist. So there is a reason why we see the stronger wave train in the northern hemisphere. But then within the tropics, yes, it's the tropical waves that are relevant. And we will study this now. So if we now look at a composite, this is now a real observed composite of a Nino. No, it's not really a Nino composite. It's a composite by using an index in we call this Nino 3.4 region. It's a region, it's a sea surface temperature index defined from 190 east to 240 east, and then 5 north to 5 south. And we take this index and build a composite of sea surface temperatures according to this index. In this case, it's just the covariance of this index. We normalize the index and calculate the covariance with the sea surface temperatures everywhere else. This is a composite if you want to. But it doesn't really give the typical size of El Nino events because this is just a little bit more than around 1 degree. It gives you more the typical size of variations typically if you take into account every year, not only El Nino years, in the tropical Pacific. But still the ENSO phenomenon is clearly popping up here. See this. But you also see the teleconnections in sea surface temperatures. So there's this famous horseshoe pattern. So you get the warming here. You can guess also this is warm up here in the North America. But then you get a cooling all around it. Interesting. Let's have a look at the, maybe we can explain some of this cooling. So this is now taking observations of rainfall, taking the same index. We now do a composite, we calculate a composite of rainfall. This is the shading here, and low-level winds. And so one of the very important ingredients that we will study later on is this local wind response that we get, this westerly winds that actually, as you can imagine, weaken the trade winds on the equator, in this case, close to the equator in this region. So in this region we have the strongest rainfall signal now due to El Nino in the central Pacific essentially. Even though the largest sea surface temperatures were in the eastern Pacific. It's interesting to think about this. Do you think you have an explanation for that? Why do we see much stronger rainfall responses in the central Pacific, given that maybe the strongest sea surface temperature response was actually probably further to the, at least extending much further to the east, but then the rainfall signal becomes weaker there? It's because of the mean sea surface temperature distribution. The eastern Pacific is simply very cold. And even if you increase the temperature there a little bit, it doesn't mean that a convective activity will be triggered, because it's still so cold. Whereas in the central Pacific, the ocean is already relatively warm. So a smaller perturbation of a temperature may be able to trigger already convection. Secondly, we can try. So the winds that we see here in the northern exotropics is of course an indication of this Rossby wave train that has been triggered. Is this strengthening, a very, very famous strengthening of the Aleutian low that is going on. And this will of course, as you can see, transport warm air into Alaska. So we can explain this with our extratropical Rossby wave train that then propagates further but loses energy. But we also see, here we are in the westerly wind regime. North of 30 north, we enter the westerly wind regime, where we have in the mean, so to the north of this high pressure here, somewhere we have again a low pressure at about 60 north, and we get westerly winds on average. But the ENSO response is enhancing those westerly winds. It's enhancing the westerly winds. Now, can you try to explain why then that means that the surface should be cool here?
So the path of these Rossby waves, which is reducing increasing the high pressure probably.
But okay. So we see that we cause a low pressure here in the North Pacific. This is a low pressure. And the low pressure enhances the westerly winds. So the wind speed, if you calculate the wind speed in ENSO years, will become larger. And this is probably something you cannot really guess, but it's very intuitively, because you know that things dry much faster. If you put them out to dry when there's a strong wind compared to not so strong wind. That will change the ocean evaporation. So the ocean evaporation will be enhanced during El Nino years in the North Pacific. And enhanced evaporation will increase the latent heat flux from the ocean surface. So the ocean cools off because we have more latent heat flux. The ocean loses more heat to the atmosphere. That's the reason we see this cooling there. Maybe if you go to longer time scales, there could be something more complex, like ocean dynamics, triggered by the stronger winds. But to first order approximation, you can model this without ocean dynamics. It's just heat fluxes are increased due to stronger winds. It's a very powerful mechanism in the ocean to cause variations of sea surface temperatures by changing the evaporation and triggering more latent heat flux in this case. And then the same may be true in this region. For the Indian Ocean, it's a mixture of processes essentially. There's some increased sinking motion here, also induced by the ENSO phenomenon. And so that may increase solar radiation, but there's also wind changes. So it's a mixture. The warming here in the Indian Ocean is a mixture of several processes. It's not so easy for this region and that region. There may be different processes. But it's interesting to study what can explain all these different teleconnected surface temperature, even simply surface temperature pictures, signatures to an ENSO phenomenon. Okay, so we want to describe this a little bit. We like equations, right? In principle, we know already everything, but now we want to make it more complicated by looking at equations. So that has been done in a very famous paper by Gill in 1980, if I remember. There are two papers, one paper by Gill and one paper by a scientist called Matsuno. So they analyzed the response of the atmosphere to an El Nino-like heating, by an El Nino-induced heating perturbation. We know the warming will trigger more convection, we have seen this, more rainfall, and the heating in the atmosphere will modify the atmosphere directly. And people have studied that in this famous paper, for example. And actually we will not repeat the calculation because it's very complicated, but in principle we can understand a little bit what is going on. Because this set of linearized equations that Gill has solved in the paper, we know already. It is our linearized set of equations that we have solved in the free case to derive Kelvin and equatorial Rossby waves. But now Gill has done something very intelligent. I think he said, oh, but we want a forcing, of course. We want to add some forcing. Now the forcing is a little bit tricky, because in principle we add to the continuity equation a forcing, which is we add mass or something like this. But the idea is actually something else. The idea is something entirely else, which cannot be done properly within the shallow water equations, but we should use really a compressible system, because we want to add, the idea behind this Q is we add a heating. And what heating does in the real atmosphere, we know this. We have discussed this already. When we have in the ENSO region upward motion, the heating due to convection will be compensated mainly by upward motion. We have discussed this because the only term really in the tropics that is relevant to cool off is the adiabatic cooling, which is stronger in that case than the advection. And that will cause upper level divergence and low level convergence. But here we see already we have both. In an El Niño event, we have both convergence and divergence. So that's the idea behind this. If you think now for a moment in a stationary state, what this Q would do, it would cause convergence or divergence. That was Gill's idea behind this. Just as we have, like we have in a real atmosphere. Only that with a constant Q, which would be an El Niño case, in reality we have divergence and convergence fields. But in this equation we can have only one. So in the paper actually he has used a trick. He has changed the sign of Q, going from the lower to the upper troposphere to represent both cases. Can be done. And then you have a forcing, and then you in that case you may have a problem that since you have a forcing of neutral equations, they may just start to grow infinitely. So you need some kind of damping. So what he has done in the paper is he has introduced Rayleigh damping terms. So on each side of the equations you add a term, actually minus epsilon u primed, minus epsilon v primed, and minus epsilon psi primed. Simple, very simple, we call this Rayleigh friction. So you take away energy out of the system in this way. And then he looks for stationary solutions, solution to this force system. The solutions that he finds are shown here. So this would be a horizontal picture of this. The heating is actually here, just in this region here at the equator. And something intuitive happens. On the eastern side, we see that there's nearly no meridional motion. So this is clearly dominated by the Kelvin waves. Only that the Kelvin waves, we don't see them anymore propagating because we are looking for stationary state solutions. So the pressure pattern, here the low pressure pattern actually on the equator, it's extending at the equator into the eastern direction through the propagation of Kelvin waves. In the model actually Gill even assumes he has an infinite domain. In the real atmosphere it turns out what can be very important is to have the fact that we have a finite domain in the zonal direction. So he will essentially cause some upper level divergence, but this upper level divergence at some point will be compensated by upper level convergence and actually sinking motion. And so that it can be very important to modify for the real world the response. But he has assumed an infinite domain where it just goes to infinity. So he has a response only very close to the source. Whereas in the real atmosphere you may see very strong responses even on exactly the opposite side of the forcing. But yeah, we are mainly concerned about the local response here. And we see something that we may identify as Rossby. These are cyclonic Rossby gyres just to the west of the heating. So these are determined by our Rossby wave solutions. So equatorially trapped Rossby waves moved in this direction and caused in the stationary state these low pressure systems here. So what is the final outcome? The most important for our positive feedback is that at the equator we get a dominance of these westerly wind perturbations going into the heating, and then weaker easterly on this side. But what will be relevant is in particular this signal here. So westerly winds on the equator. We have some trouble actually if we look at the ENSO wind response. We clearly see the westerly response here in these observations. I have personally trouble to see this kind of Gill Rossby gyres, the cyclonic gyres. I don't see them. And the Kelvin wave, since maybe ENSO is too large, we would have to go to see the Kelvin wave response here. I should have plotted maybe even until the Atlantic, because ENSO is too large scale. In order to see a nice Gill type response, like in the theory, it would be probably better to take an Atlantic Niño and look at the response to that, because the basin is smaller, so we can have a more confined response. But what we definitely see, and what is the only important ingredient here for the ENSO phenomenon, are that these westerly winds are triggered. And they are consistent with the Gill type response. By the way, the Gill model has also been questioned. There have been other papers written later that say, oh, maybe we should look at it from another angle and use slightly different equations, and so there are different proposals. But it's still, I would say, the standard assumption for adjustment to a tropical heating anomaly. So what we want to do now is, we can understand that if there's the warm anomaly, there should be westerly winds in a large part of the central western Pacific. Central, really. So for the wind response, we really have to look in the central Pacific. So the ocean has caused something to the atmosphere. Now we want to understand what this signal in the atmosphere is doing to the ocean. So we've understood that. Now we want to understand the other direction. So what we want to do is to understand the ocean response to such a wind forcing. Just a very simple analysis here. And what we do, or what I did, is I used an ocean model essentially. We will discuss this model later on, where I did nothing else. I did two simulations, almost identical simulations. The only difference between the two simulations was that I added the positive zonal wind stress in the central Pacific. That should mimic the ENSO wind response. And then look what's happening in the ocean. It's interesting, no? So what will happen? Who knows? So the ocean model that I've used, in principle, is what is called reduced gravity model, and we want to understand that now, what that is. Yes, reduced gravity model. Because again, we want to keep things simple. Of course, the real ocean is much more complicated. But the idea is the following. If you look at the mean temperature distribution that we have looked at already, or what physicists often do is, okay, this is too complicated, right? It's too complicated, the structure. What we do is we assume it's warm here and cold there. Let's say, okay, let's make it that way. You have some kind of surface, and then you have this line here that goes like this. It goes like this, and then we say it's warm here and cool there. That means there's a density ρ1 here and a density ρ2 here, that they can be different. But otherwise, we don't distinguish anything. And then there's the thermocline between them. So this height could be h1, and then this height could be h2, essentially. I think this is this is the right way to look at it. So we keep things simple in this model. And so what the problem there is, we want to derive an equation for this upper level, because we will assume in the end that the lower level is kind of without any pressure gradients, without motion, is just something that is not doing anything. But what we want to understand is what is the pressure gradient in this upper layer. So the trick is then that we again integrate. Maybe it's started before. Yes, no. We integrate the hydrostatic equation from some arbitrary position here to the height, this height in between the two, and that gives us this expression here. We calculate the gradient, and we get this expression here for that relates the pressure gradient in our lower level to the height gradient here. But that's not enough yet. Then we integrate further into the upper layer to an arbitrary height z again there. And if we do this, of course, we have to take into account that then the density has changed. So we get a different density here, but otherwise the integration is again trivial. Then, in order to derive this model, of course, you have to assume again that you get two equations, and you can merge them by assuming that the pressure here is the same in both layers. If you approach from here or the approach from there, the pressure at the boundary, there should be no jump in the pressure. So you assume it's the same pressure. So the pressure in level 1 at that height is the same as the pressure in layer 2 if we go to the same height. And that leads to this equation here that relates the pressure gradient in the upper layer to the pressure gradient in the lower layer and the pressure gradient, if you want, of the thermocline. Because, okay, we have here gradient of H2, but assuming that H2 plus H1 is a constant, it's just the height of the total system, which is an approximation, then we can express the gradient of the thermocline just by minus the gradient of the height of the second layer. So that's a trivial. So this is just the gradient of the thermocline in principle. And then we use our assumption, the pressure gradient in the second layer is just so much smaller than the pressure gradient in the upper layer that we can neglect this term. No motion in the lower layer. So of course, an approximation again. And that means that any pressure gradient in our upper layer is independent of height and can be expressed by the depth of the thermocline, by the gradient of the depth of the thermocline. Almost looks like our shallow water model, with the small difference that instead of just being density, we have here the difference of the density between the two layers, which is small. So for typical, if you insert in an ocean thermodynamic relationship, typical temperature differences between, like, what was it here, around 28, 25, 6 degrees and maybe 10 degrees or something like this, you will get that this relative density perturbation is about 1%. Only 1%. But that means when we formulate our shallow water model for this upper layer, and we know now the pressure gradient force, that means that those equations for the equator look exactly like the one that we have used for the atmosphere. With two differences. The one difference is the height is now the height of the thermocline, for which we have again a continuity equation. The mass in our upper level is conserved. We have, so high H here means the height of the thermocline always. But G is called reduced gravity, and G is simply G primed is G times rho 2 minus rho 1 divided by rho 1. So this relative change width is about 0.01. We just take it as a number. But then these equations exactly look like the shallow water equations. And we do something else. We add a forcing term at the surface of these equations. So the forcing term is expressed by this tau y in this case and tau x in the U momentum equation. Thermocline. Wow. Where does that come from? They listen to us. What is the thermocline? Why did that pop up? I have no idea. Anyway, tau. So we have tau x and tau y, the zonal wind stress and a meridional wind stress. In our example, we will just use the zonal wind stress. In reality, there would also be a meridional wind stress. So if someone wants to refine the analysis, you would have to include that. Before we look at the solutions, by applying numerically in that case, by applying this wind stress, we look at what is happening in a stationary state, motionless stationary state. In a motionless stationary state, everything goes away, apart from this pressure gradient term and the forcing term at the surface. And we get an equilibrium between pressure gradient or tilt of the thermocline and the applied surface stress. This is a very useful equation, and it explains already immediately that within this model we can nicely explain why, given that the fact that we have trade winds, the thermocline should be tilted, because it's written here. If there are zonal winds, then the thermocline should be tilted. So we can explain this. It's nice. You will do this in an exercise actually to integrate this equation. For see if we can reproduce the numbers more or less. Thermocline in the Western Pacific 150 meter, thermocline in the Eastern Pacific maybe less than 80 meters. Can we reproduce these numbers given some realistic wind stress assumptions? Okay, now in the numerical model that I have, it's a reduced gravity model, so the model is this essentially. However, because people have developed this model to couple it, to build the first coupled models, ocean atmosphere models, to simulate ENSO, really the ENSO coupled phenomenon. The problem with this coupled model is you get nice thermocline variations if we have wind stress variations. The problem with this model is there can be no feedback to the atmosphere, because we are never, the density in principle, the density in this layer is a constant, and therefore the temperature should be the same. So we don't get any temperature variations in theory. However, in this model, this is a little bit relaxed. So there's an additional, in the real model, that are still called reduced gravity models. We say, okay, this is an approximation. Yes, the density is about constant, but still we allow for temperature calculation. So there are temperature calculations. In one term, for example, could be vertical velocity delta T divided by the thermocline, essentially. So some parameterization of processes that may change the surface temperature. So if there's a mean upwelling And if there is a reduction of the thermocline depth, then that will change our surface temperature if you assume that the temperature at the thermocline is a given quantity. Plus, of course, in that case, we can also induce horizontal advection terms. And so on. So there's an additional equation for the temperature that parameterizes some effects of the shoaling of the thermocline, which can be determined by this pure reduced gravity model. So we take this model, do two simulations I mentioned to you, two simulations. One simulation is just a control simulation, and the other is the only perturbation I've put is this wind stress. And we look at the response. And after 1 month, this is the field of the thermocline depth, we get this response here. Look how beautiful this is now. This really looks like a Kelvin wave that propagates to the east, and the Rossby waves that is still strapped at the equator that propagates to the west. So in the ocean we can do this, in the atmosphere not. If you take a month's time for the atmosphere, everything will be already, they move much too fast. But in the ocean, you will calculate the phase speed in an exercise. It's after 1 month you get this response. And then you can integrate further. Just always having a persistent this forcing there, where it's never changed. The forcing is not turned off. And after 4 months we get this picture. Probably after 6 months we get the strongest response. So there's some cycle in the response, some overshooting. You see? Strong response. It seems that now the Kelvin waves actually have transported the signal to the very East Pacific. And in the model what they do is they seem to transform into coastal Kelvin waves. They kind of go along the coast. They like to do this, these perturbations. They transform into coastal Kelvin waves and transport the energy to the north and to the south. Whereas the Rossby waves have reached this other boundary of the basin and then are kind of reflected and complicated things happen. The interesting thing is, then the stationary state looks a little bit weaker, so I can just integrate as long as I want. The model never crashes. But let's say if I look from 2 to 4 years, I have something like the stationary, reach the stationary state. And it's just interesting to see how well this equation, du by dh by dx, 1 over h tau x, what was it? How well this equation is valid even in this case. Because we get a thermocline tilt, a change of the thermocline, only where we have applied our wind stress forcing, d tau by dx. Otherwise, the thermocline, as you can see here, is constant. But this leads to an interesting teleconnection, because our signal, the thermocline perturbation, goes away 10,000s of kilometers. We have this response here, due to the simple fact that in the end our waves will guarantee that this equilibrium is mainly reached. So we get still the signal at the very, very East Pacific and at the very West Pacific of our thermocline perturbation. From a wind stress forcing that was just in the Central Pacific, a Gaussian applied to the Central Pacific. It's an interesting teleconnection. So for the H field, this is unproblematic. We could have solved the equation that we have posed here. But in the model then the temperature is also calculated. So using such an equation we get a temperature signal. And the temperature is evolving slower actually. The reason is that after 1 month we see nothing essentially, very weak signals. The reason is that the signal is so close still to the forcing region and the surface and the thermocline is so deep that the temperature signal has not reached yet the surface. The temperature signal reaches the surface only later on. And there are actually two things that is happening. At the forcing region itself, we get a warming, which can be understood by the fact that since we apply a westerly wind there, then that causes Ekman convergence and downwelling. So that would cause kind of this effect locally at the equator. But then we see a remote effect through the thermocline change. So the Eastern Pacific, it's warming because the thermocline gets deeper. That is the signal that we have seen. So here, this is a local effect due to change of upwelling, and this is a thermocline effect. And then after 12 months we see this, but then we see also it decays a little bit. In the end it becomes slightly weaker, and we get some cooling in the Western Pacific. So this cooling signal in the Western Pacific that we have seen in a Niño event is due to this change of the tilt of the thermocline, at least parts of it. Our horseshoe pattern had a cooling signal also close to the equator. The extratropical is probably evaporation changes, but the tropical one could be related to changes of the thermocline. So now we have understood, so now the feedback cycle is closed. We have warmed the Eastern Pacific, which has caused the westerly winds. And the westerly winds cause to warm the Eastern Pacific even more. It's a positive feedback loop that we have found here. And this, the time scales, you can look at the time scales of this, is about, of these developments, is about months to almost 1 year. So to get really the signal fully evolved, we probably need 1 year. So that explains part of the reason why ENSO is such a persistent phenomenon, because it takes so long time for the waves to carry the signal through the whole Pacific basin in the subsurface. So then the question is, of course, okay, so this is now a positive feedback. Why doesn't this just explode? I mean, positive feedback means that it should grow and grow and grow and grow and so on. Of course, there are many, many reasons, and in reality there will be damping terms in our equations that we haven't shown, of course. There will be numerical damping in the model, but in the real world there will be frictional terms, right? When the velocities get too large, there will be frictional terms that kind of reduce the velocity. But that wouldn't be able to, ENSO phenomenon is not a real, it's called El Niño Southern Oscillation, but it's not a real oscillation, Do you know on what time scale, more or less, we find the largest energies?
4 to 6 years.
Something around this, 4 to 7 years probably. So that's the typical period. But that doesn't mean you get a spectral peak. So it's not like a harmonic oscillator, but you get kind of a broad energy maximum, but with kind of clearly increased energies in the 4 to 7 year range. But a frictional force would not be able to explain such an oscillation. So this oscillation, and there are two types of theories, but they have been already converged in the literature. There's one theory called delayed oscillator, which says that, it's actually what makes the signal reverse is actually the waves here that reach the equator that are reflected, then these Rossby waves are reflected as Kelvin waves, and they tend then eventually to cool off, and we see this maybe a little bit in this decaying phase, they tend to cool off a little bit the equatorial region again, because they propagate as Kelvin wave all the way. They tend to cool off eventually. But of course, if we don't change the forcing, that would lead to less forcing in a real coupled world, and then maybe that could lead to an oscillation. This is one theory. It's called delayed oscillator theory. It's a very famous paper on that, on ENSO, basic ENSO theory. They derive a very simple set of equations. It's just one equation, but with a delay effect. Therefore, delayed oscillator. And that can cause this an oscillation. And they try to argue what should be the time scales here. The other theory is that ENSO is just, it's not an oscillator, but it can be triggered, and then it's then damped away. But it's kind of it's a forced oscillation. So sometimes you trigger it, and then you get the positive feedbacks, and then there can be some weak tendency for oscillation. But you always need some kind of forcing to trigger it. And a third theory that is more closely related to the delayed oscillator is recharge-discharge mechanism. So the idea is then that the meridional energy transport is also important and causes to some overshooting at the equator. So the energy is kind of transported then by all kind of waves, by Rossby waves also, into the meridional direction, and it's causing some overshooting. So it causes at some point a cooling actually at the equator, a small cooling that then triggers our positive Bjerknes feedback and causes to a La Nina development instead of El Nino phenomenon. So it's a very interesting theory still going on. Next year we will have a ICTP workshop on ENSO theory, actually, ENSO theory and teleconnections. So it will be important researchers in that field will be coming to ICTP and we'll give also lab sessions on small little toy models how to simulate the ENSO phenomenon. It's quite interesting because it's really the only very well understood climate oscillation on the interannual time scale. I mean, Rossby wave we understood quite well, but this is really on longer time scales the only phenomenon that we believe to understand relatively well. Even there are still competing theories, but more or less the theories are converged. I mean, there are no doubts about what we told today, this positive Bjerknes mechanism. There's no doubt about this. Then why it's oscillating, there are still discussions. And, it's maybe not yet 100% sorted out, but still it's the best understood phenomenon on longer than weather time scales, let's say, or intraseasonal time scales that we have here. And as I mentioned, in the Atlantic, there's a similar phenomenon. We could have done the integrations in the Atlantic, which is called Atlantic Nino. And it has similar properties, but you can see the basins are very different in size. So the time scales will be very different from what we have seen here. And it's also there discussed what are the main mechanisms contributing to it. Yeah, it's interesting to study this phenomenon. Yeah.
Is it possible, or anyone even tried to reconstruct new events in the past from proxy data?
Yes.
So
People have done that.
have they seen whether there were these new events in interglacial periods?
Good question. I think there is. I cannot answer this question, but I think there are studies that say ENSO has changed a lot in the Earth history if you go back in time. I think there's a clear indication that if you go very long time back, when maybe the thermocline in the Pacific was very deep, there were no El Niños at all. The whole Pacific was so filled up with warm water when levels of CO2 were maybe 16 times that they are today. So if you go really back to the early parts of the Earth, then the assumption is there was no El Niño at all. So El Niño is a relatively in terms of the history of the Earth, relatively recent phenomenon. And there are choral reconstructions of that, definitely. Not that I'm not very much of an expert on that, but they are. And of course, it's a very, very ongoing, heated discussion. What will happen to ENSO in future? Even more speculation. I mean, models, you can imagine, you have heard about the IPCC process where all climate modelers come together and use all available models to make assessment for future climate. All models show a warming, right? Because of increased CO2 scenarios, but what they do for ENSO is just all over the place. Some models do this, some models do that.
Do you know about any papers regarding teleconnections between the Pacific and Antarctica?
There are also plenty. Antarctica, there are plenty. There's a very strong teleconnection actually. They are very highly, the Arctic oscillation, for example, which is, and ENSO, they are much more highly correlated than the northern, what is called northern annular mode and ENSO. Yes, there are studies and I know that there's a strong connection. So warm ENSO event would lead to a negative phase of the southern annular mode or something like that. But there are studies, but maybe not so many. But yes, I'm aware of some studies. We can discuss these. Yeah. So this ENSO teleconnections are really, if you go to the literature, thousands of papers trying to pinpoint new ways of teleconnections. And we will in the next lectures, actually, we will sometimes continue to come back to this, but it's such an important phenomenon that may help us to predict climate for the next season that it's useful to understand all the possible teleconnections. Yes?